Good morning, everyone. I want to welcome you to another statistical class. Today, the focus is going to be on math review. I'm actually going to tell you significance of doing what we want to do today. Let me tell you this. Uh, the reason why the method of statistics and method in machine learning are very attractive is because of the fact that there is mathematical knowledge embedded. So, and that is why um, the role mathematics play in statistical analysis in machine learning algorithm cannot be overemphasized. What you're going to be seeing today, of course, you've seen them before. Okay, you've seen them before, but I'm just going to be pointing to the connection, what you're going to be doing today have with the techniques that you actually going to be using when it comes to statistical analysis. So somebody once said, do we do mathematics for fun? And I'm going to say, no, we don't do maths for fun. Okay. All mathematical efforts are targeted towards improving the quality of life. Okay, so this same material, we're still going to use it on Friday. Wherever we stop today on this material, we're going to continue on Friday. Now, today, I'm going to start with vectors and matrices. I introduced to you the nature of data set. You know, the data set arranged in row and column, the same way matrix is also arranged. Okay? If we really want to understand, the data structure, if you really want to conduct a meaningful statistical analysis, of course, because we're going to be working with data frame arranged in row and column, the method of matrices and vectors become necessary. And that is the reason why we're going to go over vector spaces and matrix operations. And not only that, today, I'm going to walk you through what we call matrix decompositions. Let me tell you this. The idea of matrix decomposition is very, very useful when you want to talk about matrix completion. We are, we got some missing data, and we actually want to estimate the missing data, or we want to talk about image processing, face recognition, and so on like that. Matrix decomposition. Okay, where we have the aging decomposition and singular value decomposition become very, very crucial. We're going to make use of them. And lastly today, okay, I'm going to talk about, briefly introduce you to random vectors, where we're going to talk about the mean vector. We're going to talk about covariance matrix. Where the other one, the outline number 4, that will be achieved on Friday. Now, what I need from you today is just to make sure you sit back, try to ask questions where necessary, even though I know you've seen this before, you've done something about this before, but you may be doing that just for doing sake. You may not be able to know the connection what you were doing have to statistical analysis and to machine learning algorithm. I'm going to start with a vector. Okay, there's a difference between vector and matrix. Okay, now this is the way vector look like. If you take a look at X and Y, you have a singular column, okay, And in the X, you can see X1, X2 up to Xn. That may be representing something. And you see Y1, Y2 up to Yn. Vector is when you want to look at the dimension of a vector, depending on the number of items you have. Right now, we got n number of items. That will be n by 1. Okay? But matrix on the other hand, we don't talk about something by 1. Okay? The numbers of rows and the columns, at least each have to be greater than 1. If you take a look at matrix A right now, take a look at matrix A. Okay? That is giving you n by n. I need you to be relating that to your data frame where they have features and number and observations. Okay, observations in the row, features in the column. Okay, that is more or less of a typical matrix or representation. Okay, so take a look at that. So there is a difference between a vector and matrices. And let me tell you this. When you are working with the multivariate data, right? Multivariate data, they have so many variables. Okay, the idea of vector will be used when you are interested in only the means. Because you have multivariate, we have so many variables. You may want to know the mean of each of the variable, and that will be represented in a mean vector by a mean vector. But if you want to talk about the covariance structure of a matrix, what do I mean by covariance structure? Let me tell you this. I'm going to tell you this. I understand my mathematics perfectly. I understand my mathematics perfectly. You know why I understand them? I understand them because I link every symbol, every notation to real life situation. That's how I understand my math. And that was why I'm challenging you now. It's not just by doing math, but trying to understand what is behind the scene. There's a story behind the scene of equation, which you need to be able to identify. Okay? And we don't just do what we do. We got a reason, okay, for doing what we do. Now, if I want to talk about matrix now, okay, like A, n by n, I can actually link that to covariance matrix. In the covariance matrix, we're actually going to have variances as well as the covariances. And that is why, okay, the idea of matrix is actually one of the reasons why matrix has application in statistics. We're never going to touch them if they don't have application in statistics. So this is n by n. Take a look at that. Is there any question on this page before I move on? Is there any question on this page? Any question? Anybody? You all good, right? Okay, do not hide your feeling. Okay, if you don't understand, ask question. Okay, now I'm going to go to the next one. Where am I going now? Okay, oh my God. I'm actually going to another form of a matrices that we call identity. Take a look at that. Identity is a matrix. Okay, it's a square matrix, n by n. Square matrix, the numbers of rows and the numbers of columns are the same. But why is it an identity matrix? It's because if you look at the diagonal, you're going to have 1, 1, 1, 1, 1 or 2. And half diagonal, they're all going to be 0 entries. Okay? Identity matrix is as a significant, basis when it comes to statistical analysis. Okay? So, and if you want to look at it from a scalar point, it's like talking about 1. Okay, it's like now in a multiple point, you have 1 is so many more, 1 is so many times. Okay, so very useful. Now, the next thing I'm going to go into now Like I said, we're trying to review. We're having a math review right now. Now, the next thing that I want to talk about is matrix multiplication. Okay. Why do we need matrix multiplication? Okay. If you are into face recognition, image processing, or maybe you're trying to use the idea of a singular value decomposition, okay, or you try to use the idea of a low rank, the blah blah blah, and so on like that, you're going to see yourself multiplying matrices together. The approach will involve multiplying matrices, okay, and that is the reason why we need to understand the mathematics around that, multiplying matrices together. Imagine we don't know how to do that. There's no going to be a way to be able to perform our statistical analysis and get results. Let me tell you something. When you are into regression analysis, I'm going to be specific right now. Maybe you're trying to look at, oh, let me remember what I did in my bachelor project. I look at the effects of inflation rates, exchange rates, consumer price index on the gross domestic products of Nigeria. That was what I did. That's a multivariate analysis where my intention was actually to isolate effects, the role of each of the explanatory variable on the response. And let me tell you this, if you know what is behind the scene, getting that, it will involve a matrix multiplications for you to be able to figure out regression coefficients. If I want to figure out regression coefficients, if you look at what is behind the scene, even though some of you will say, okay, I'm going to use computer. There's a lot of things behind the scene. Formula has been programmed in the computer. Or the computer can't just do anything without something being programmed mathematically. But why do we need to worry about the way it is being programmed? Is because things are changing in life. And that if things are changing, situation is dynamic. If I understand the basic fundamental principle around the formula that we are using right now, if I understand that, then I will be able to modify that. You may not be able to successfully modify or adjust something you don't understand. Does that make sense? Okay. Multiplication of matrices is very, very crucial. You can see here I have a matrix A of dimension n by m. The first n represents the row, and the m represents the column, the number of columns. And we take a look at B. We have m by k. Multiplying them, okay, you're going to see m canceling m. M is going to cancel m. And at the end of the day, the new dimension, the dimension of the new product is actually going to be n by k. Look at that. And that was why this guy here is n by k. Okay? So take a look at that. We may not be able to make a sense of what we have right now until we get to application. But what we're trying to figure out right now, we need to be able to understand how this is done. Understanding how this is done, the next thing that you're actually going to see, you're going to see them in the formula to achieve a particular, maybe explanatory goal or predictive goal. Okay. Now the next thing I'm going to talk about now, after the matrix multiplication, okay, is to talk about the transpose. Let me go to transpose first. And the area that I want to talk about now It's actually very, very crucial. Okay, I want to talk about transpose of a matrix. What do I mean by transpose? Or by what do I mean by matrix transpose? Sorry, this is kind of too fast. I think I'm going to 1 minute. Okay, so when we talk about matrix transpose, I know you've done this before. You know, matrix transpose is more or less a way of changing or rearranging data structure. Oh, initially I actually have observation occupying the row position, and I have the numbers of features in the column position, and I decided to change the position. Changing the position is trying to rearrange the data structure for better analysis. Okay, now initially, if I have a matrix A with n by n dimension, okay, if I obtain the transpose of the matrix, okay, then the dimension will be reversed. Okay, initially it was m by n. Okay, it's actually going to change to n by m. We got reason why we do transpose. Let me tell you this. I'm going to write this for you. Give me 1 second. I'm going to write this for you now. If I have y equal x beta, okay, plus the error. This is a specification of linear regression model. The y is a vector. Y represents response. X is a design matrix. Okay, and beta that you see is actually going to be a vector, beta 1, or maybe from beta 0 to beta 1 up to beta k, that we call regression coefficients. Okay, and of course E is the error. Okay, you normally say this in a typical linear regression model. This is that is a matrix specification of linear regression. What do you think I'm looking for? I need you to take a look at the beta cap. The beta cap is an estimated regression coefficient. If I want to be able to get that, oh my God, I needed to see what is at the right hand side. You can see the transpose of X. I need to get, from the design matrix X, we need to find the transpose of X. After finding the transpose of X, we're going to multiply the transpose of X by S, then getting the inverse. After getting that, we're going to multiply by S transpose Y. If we're not able to obtain the transpose, there is not going to be a way forward. If there's no way forward, there is no way we will be able to isolate effects of a particular variable on the response. And that is the reason why mathematics actually play a very huge role. Now you can see matrix transpose. So transpose is very, very crucial. Okay, now I'm going to move right now. Now, I'm actually going to move to the properties of transpose. Okay, for instance, if I have a matrix A, I take the transpose of matrix A, and I also take the transpose of a transpose. Taking a transpose of a transpose, what the first one is trying to say, what this guy is trying to say, is that I'm actually going to recover my original matrix. Taking the transpose of the transpose. I have a matrix A. I take the transpose of that, and I say, okay, I've changed the structure. Can I have a way to go back to my original data frame? Oh, okay. What are you gonna do? Why can't you take the transpose of the transpose, and that will return you back to the original data set? Now the second one here is trying to say, okay, you know what? If I have two sets of matrices, matrix A and matrix B, if I add them up and I take the transpose, it is the same as four of us taking the transpose of each, then add them up. You're actually going to get the same result. That has been mathematically established. The third one is trying to say, if I do matrix cell multiplication and I find the transpose of the resulting matrix, it is the same as, you know, taking, when you take the transpose of H, okay, pre-multiply the matrix by the transpose of B. Let me tell you this. When we are talking about matrix multiplication, commutativity may not work. A multiplied by B may be different from B multiplied by A. Does that make sense? Okay, so if I were you, you can try to verify these properties with you know, matrix example. Okay, you can verify that. Now we're moving gradually right now to something fantastic that I'm actually going to call norm and inner products. Okay, now let me tell you this. What we want to do now is actually very, very crucial. Okay, not only to statistical analysis, but machine learning algorithm. We want to talk about the norm and the inner products. What do we mean by norm? What are we trying to achieve? Oh, we're working with a vector, right? We're working with the matrices, right? Is there a way to figure out the length of a vector? I want to know the length, or I want to know the distance. Why am I interested in knowing the norm and the inner product? Is because, let me first talk about the length. I want to know the distance. I want to know the length of a vector. What am I going to do to be able to understand that? Not only that, I'm interested in, maybe I'm actually working on optimization problem and I needed stability. How am I going to achieve the stability? Okay, the norm and the inner product will enable us to be able to figure that out. And let me also tell you this. The inner product that you see will actually enable us to have a definition for a very important feature that validates, or that, don't let me say validate, that simplify what we do in statistical analysis, that I'm actually going to call orthogonal. You're going to see the role the inner products play in orthogonality. I'm also going to tell you, what do we mean by orthogonality? I'm still going to go there. But let me start with the vector norm. By vector norm, okay, This is a mathematical notation, okay, by vector norm. We actually have a function that assign a non-negative value. Because if I want to figure out the length, it's either the length is 0 or it's greater than 0. We don't want a situation where the length is going to be negative. And therefore the norm, that's why you see the norm is going to tell you, you know what, if you want to go by scalar, why can't you square each of the observation? After squaring them, add them up. Why are you squaring them? Oh, because I don't want negative. Because I'm interested in the length. The length cannot be negative. Does that make sense? Okay. Then, we square them. We add them up. But we're gonna sit again and say we square them because we don't want negative. We add them. Does that really make sense? Oh, there's something we need to do. Because the units of x1, x2 up to xn may not have the same unit when you square. But what do we need to do? Oh, this is the reason why in statistical analysis, we normally use standard deviation instead of the variance. What is the difference? Oh, variance as a square unit. If I'm working with dollars a month, the unit of the observation, each observation is the same as the unit of the mean. But when I find the variance, the unit is going to be dollar squared. It doesn't make sense. Oh, what do I need to do if I want to have a measure that will have the same unit as the mean? Then I need to find the square root. Statistics is like a story that goes on and on. We don't just do what we do. We got a reason why we do what we do. Now, that is the essence of the square root. Okay? Now, finding the square root, then what we have will make sense. Now, in a matrix form, s1 squared plus s2 squared up to sn squared is the same thing as a matrix multiplication of the transpose and the original. So S transpose, the transpose of S multiplied by S is the same thing as S1 squared plus S2 squared up to Sn squared. Does that make sense to everyone? Okay, now we're moving to inner product now. Why do we need inner product? Oh my God, we need inner product for a lot of stuff. The inner product will enable us to define orthogonality and orthonormality. I'm actually going to tell you what is the meaning of orthogonality and orthonormality. Okay, I'm going to tell you the meaning. But let me first talk about the inner product. When you take a look at the inner product, that is another matrix multiplication. The matrix multiplication, and in the structure, you can say the transpose of X multiplied by Y. Imagine if you don't put a transpose, you just multiply X by Y. That will be complicated. What is the significance of transpose? Then transpose induces simplicity into the computation. Does that make sense? Without transpose, we're actually going to have a complicated multiplication. Now, I needed to take a look at this now. X1, Y1, X2, Y2, S2, Sn, Yn. When you take a look at that we go a long way in trying to define something that we can call independence of variables. And that enable you can see the result at the end of the day. It's also linear, right? Linear, right? Take a look at that. Okay, now going to the geometric interpretation, the combination of a inner product and the vector length will enable us to be able to capture angle between two vectors. At times, the interest, when you take a look at computer graphic, okay, angle representation is crucial. How are they going to have an accurate measurement of the angle between two vectors? That they need to do this. Take a look at that. The cos theta is actually, if you take a look at the numerator here, is the inner product, right? They're divided by the vector norm of each vector. I mean, the norm of each vector. Does that make sense to everyone? Okay, now I want to go into orthogonality. Let me tell you this. What make our models to be a good model? If I want to trust my model, then it means assumptions hold. If you are performing a relational analysis, situation where you are looking at the effect of some variables on a response, we got a lot of assumptions. Okay, and one of the assumptions is that your variables should be orthogonal. Orthogonal. What do we mean by that? Oh, when variables are orthogonal, it means in regression analysis that would prevent the problem of multicollinearity. Has anybody heard about multicollinearity problem? The multicollinearity in statistical analysis is when a relationship exists between the independent variables that we also call predictors, that we also call features. Assumption is that there shouldn't be a relationship between them. Mathematically speaking, when X and Y are orthogonal, if I really want to know, okay, then that very inner product must be zero. You see that inner product? S transpose Y, the multiplication, that has to be zero. If that is zero, then it means in a situation where you are performing relational analysis, a particular variable will not influence the other. And what does that mean? The interaction effect equal to zero. That is what it means. When interaction effect equal to zero, your model will be very simple to compute. But imagine situation where one variable in the predictor is influencing the other. That will be complicated. Does that make sense? Now, another important property, orthonormal. There are two things in orthonormal. Number one is orthogonal. And you can see the orthogonality is when that guy equal to zero. Okay, the orthonormal now, it's already orthogonal. It's also normal. What am I trying to say? Normal? Oh, what I'm trying to say now, I'm now putting into consideration the probability distribution of it. And in statistical analysis, normality facilitates standardization. And when you look at a standard normal distribution, the mean is zero. Okay, the variance is 1, right? And that is why if S transpose S equal to 0, okay, and the norm equal to 1, oh, 0, 1, okay. This is synonymous with what we see with the standard normal distribution. So orthonormal as a property is very, very crucial. Okay, what is the next thing I want to talk about? The next thing that I want to talk about right now, okay, is talking about determinant, the trace, and the norm. Okay, I got a square matrix. Okay, of course, I want to find the determinant of the matrix and what is the significance of doing what I'm doing, of finding determinant. Oh, if I have a 3 by 3 matrix, for instance, okay, if the rank, we expect the rank to be 3, for 3 by 3 matrix to have a full rank. Having a full rank, okay, if it is 3 by 3 and the rank of the matrix is 3, then it means find the determinant, okay, you are not going to have 0 for the determinant. Because situation where you got 0 for the determinant, there's going to be an issue. We normally call that singular. Okay? So if the determinant equal to 0, okay, there's going to be an issue. We may not be able to find the inverse. Okay? Because the inverse of a matrix also depends on the determinant of a matrix. If the determinant is singular, singular means that matrix does not have a full rank. And because of that, the determinant equal to 0. Okay? And that has implication when you are trying to figure out the parameters of linear regression, because we expect, don't forget the formula that I showed you the other time, you need the inverse of S transpose X. And before getting the inverse, if I want to go by mathematical way, I need to first of all get the determinant. And the moment the determinant is equal to 0, we may not be able to find inverse. Now, if I have matrix A and B, and I multiply and I find the determinant, it is the same thing as getting the determinant of A separately, determinant of B separately, multiplying them. What I'm going to advise you to do is to verify all of this, okay? Verify them. Now, we're going into trace. You know, trace is more or less like an addition, okay? It's an addition. For instance, you know, in the matrix A. And what are we adding? At times you had something in the diagonal. Oh, A11, A22, A33, A44. The situation where a particular cell in the matrix have the same number of row and column, that would be the diagonal. You are adding the diagonal up, the element in the diagonal up. That's what we mean by trace. That's what I see here, trace A. But this time around, I'm focusing on a square matrix. In statistical analysis, we focus on a square matrix because we believe, let me tell you this, even though design matrix X may not be a square matrix, what is design matrix X? Design matrix X, we may not expect to have the number of observation may not be the same as the number of features, but there is something that will enable you to have a square matrix when you do the transpose of X multiplied by X. That is always going to be a square matrix. Does that make sense? That's going to be a square matrix. Okay? You can investigate, you can verify all those properties. Now, let me see. Okay, take a look at this. We talk about matrix right now. We talk about the trace, and let me also show you this. We also have what we call matrix norms. Okay, and I want you to see that at times we may be focusing on the trace of matrix A, and at times the focus may be on something else. The interest may be on finding the trace of two matrices that have been multiplied. For instance, I got matrix A and it's transpose. That's why you see A transpose T. Okay. Of course, after multiplying that, that's going to give me another matrix. I can also find the trace of that too. Okay. And finding the trace of that, it's more or less like, of course, A transpose AT is more or less like an A squared, right? It's more or less like an A squared. Now, in the diagonal, it's like you are adding something squared. Look at that. You are adding something squared. Oh my God. What are you adding? You are adding A11 squared to A22 squared until you get to, the last one. And that's what we mean by that. So what have I been doing right here? I've been trying to now the same thing also go with the matrix inverse. Okay, we need the inverse of a matrix. And let me also tell you this. If I find the inverse of a matrix and I multiply the inverse, I use the inverse to multiply the original matrix, or I use the original matrix to multiply the inverse, that will give me the identity that I have here. Okay, that will give me the identity that I showed you the other time. Okay, now if the column row of A are linearly independent, you know what we mean by linearly independent? When the orthogonality is achieved. Does that make sense? When they are linearly independent, then it actually means the matrices are full rank. Okay, linearly independent. Now, if it's a linearly independent, the matrix is going to have a full rank, the determinant will exist. The moment determinant exists, then the matrix is invertible. Okay, but otherwise, it is singular. When determinant is equal to 0, then the matrix is not invertible. There may not be a way forward, using this. Okay, now the properties right now, the inverse of the product of matrix AB equal to that, you can verify all of that. Now, orthonormal matrix. Okay, if I ask you to verify, or if I give you a matrix and I say, okay, can we say this matrix is orthonormal? What are you going to do? To be able to know whether it is orthonormal, find the transpose, keep that aside, find the inverse, keep that aside, then compare them. If they are the same, then that matrix is orthonormal. Does that make sense? Okay, that is how to know. And you know what we're trying to achieve with that. Now, the next that I want to talk about is eigenvectors and the eigenvalues. Please watch out. In principal component analysis, we make use of the eigenvalues and the eigenvectors a lot. In singular value decomposition, we make use of it. In matrix factorization, matrix completion, we make use of that. Okay. Now, the eigenvalues of the eigenvectors, we have an equation, and of course, the lambda represent the eigenvalues that we're trying to figure out if we're able to solve this particular equation. Okay, now the determinant, of that, we call this a characteristic equation, and at the end of the day, the values of the lambdas that we have, if you have 2 by 2 matrix, then you're going to have 2 forms of lambda. If you have 3 by 3, that will be 3 forms of lambda. And of course, in principal component analysis, they are acting like variances. Okay, the first one is going to be greater than the second one, and so on like that. Okay, now, so what of the situation where the transpose of a matrix equal to the original matrix, we're actually going to call that symmetric. We expect our design matrix in statistical analysis to be symmetric. Okay, we expect that to be symmetric. Now, we can also find the determinant of A is multiplication of the eigenvalues lambda 1 to lambda n, and the trace of A is adding them. Because the lambda 1 to lambda n, they're going to occupy the diagonal of a matrix. Okay? And A is positive definite, situation where all the eigenvalues are non-negative. They are greater than 0. Okay? And for not, so which means that's why I call that. Therefore, non-negative definite, lambda greater or equal to 0, because lambda can be 0, can be greater than 0, but if it is strictly greater than 0, we call that positive definite. Okay. Now, if you take a look at what I have here, okay, we use this a lot. If you take it, I'm actually going to quickly talk about this before I go, because I'm going to stop at page 10 today. Okay, now take a look at this. If X is an eigenvector, let me tell you this. Before finding eigenvector, we first find eigenvalue. Okay, but you know what? You don't need to worry too much. We're going to make it of R software. My TA will walk you through. And that was why the assignment that I gave right now, I said, use R. Okay? I'm not going to appreciate if you don't use R. If you just solve that manually, I'm not going to appreciate that. I want you to use software to do that. Does that make sense? And also I say use R. Okay. Now, this is actually explaining the way of getting the eigenvector. Okay? And that is only possible if your Q here is invertible. We got a lot of conditions associated with invertibility. Okay, invertible means, oh, the inverse exists. Okay, when that happens, then we say A is diagonized, otherwise A is not. Because for you to be able to achieve what you want to achieve, okay, this has to happen. And I said, your canonical eigenvectors have to be orthonormal. We know how to verify the orthonormality. We expect the transpose of V to be the same as the inverse. The moment all that is okay, do you know we are now ready for aging decomposition? Oh my God, when I talk about aging decomposition, we're actually going to use that in face recognition. We use this approach a lot, where we decompose a matrix. You're also going to use it in single value decomposition. Okay, the eigenvalue and the eigenvector play a very huge role. Okay, I think I put an example for you there. You know what? I think I'm going to stop here. I'm going to continue on Friday. Is there any question before I go today? Okay, make sure you all stay safe and have a lovely day. Bye for now, everyone.